And we're live. All right, chapter 7, which is on page 206 in your text. Continuous probability distributions. Now, in this chapter, if you want to highlight, we're going to be covering the first 3 learning objectives. All right. Now, last week, what did we talk about?
Probability.
Probability. Carrying over into chapter 6, we specifically talked about discrete probabilities. Chapter 6 introduced you to 3 types of discrete probabilities. Binomial, hypergeometric, and Poseidon. Now look, these distributions are based on discrete variables that can contain only specific values. That's what's unique to those. And consider an example of a survey of where you wanted to go out and find all of the companies that were launched in 2013. And today in 2017, you go back and you look at what companies continue to operate. So let's say, for instance, that 50 companies were started in 2013. How many companies can only be operating today in 2017? Max of 50. Can there be 42 and a half? Can a half of a company operate? No. Could the number be -3? No. You know it's discrete in that it's going to be a whole number somewhere within the range of 1 to 50. It's going to be one of those variables within that range. Now in chapter 7, we're going to start talking about a continuous probability distribution. How does a continuous probability distribution differ from a discrete probability distribution?
It changes.
I think it can write with decimal.
What do you mean it changes?
It doesn't stay, it's not more broad, it changes. It's flexible. I'm just guessing.
Let's not guess.
Okay.
Tell me, Deborah, how does a discrete probability distribution differ from a continuous probability distribution? Someone help her.
It's continuous, it's usually measuring, such as distance.
An example, measuring distance what?
That's what I meant. That's what I meant. And weight, weight of individuals and amount of bonuses earned in CEOs.
Amount of bonuses. Okay, let's look at the amount of bonuses earned by CEOs. Yes, if you went out and looked at the, let's say, the top 500 companies here in the United States, if you wanted to look at the average bonus of that individual, you would find a range that he or she, you would have a minimum and maximum range that he or she earned. But it could be anything along that spectrum, anything along that range. It could be, if the bonus was 10,000 up to 10 million. It could be anything from anywhere in between. It could be 9.5 million. It could be 9,453,072 cents. can be anywhere. It's continuous in where it can be. It's not discrete in that it's going to be a single variable. Okay, in chapter 7, this is where we are going to start. So let's look at the first learning objective, the uniform probability distribution. We're going to say perhaps this is the easiest to understand of all the continuous distributions. And if you look at the chart, is that better for your view, Wisconsin?
Yes, much better, thank you.
Okay. I knew something didn't look right. That was the glare coming off of the projector. All right, so let's look at, let's flip the page over to page 208. And if you see the distinction, all right, so for a uniform probability distribution, the distinction is rectangular in shape. So we have draw a rectangle. And what's the characteristics of this rectangle? Let's draw it further out. All right, now what's the characteristics here? How are we defining it? By points A and B. Let's throw some shade on this. Rectangular in shape and defined by points A and B. Point A, this is your minimum value. And point B of the data would be your maximum value. Now, knowing the minimum and maximum, we can define the probability function and calculate the mean, variance, and standard deviation. So if you know this is your probability distribution and you're given points A and B, you can calculate the mean, the variance, and the standard deviation. All right, at the example on page 208, Southwest Arizona State provides bus service to students. On weekdays, a bus driver arrives at the North Main Street College Drive stop every 30 minutes. Students arrive at the bus stop at random times. All right, so we have buses arriving to pick students up. They are arriving every 30 minutes between the hours of 6 a.m. and 11 p.m. Students are going to arrive at the bus stop at various times. The time that a student waits is uniformly distributed between 0 and 30 minutes. So this is what we're given. And it says that we are to draw a graph of this distribution, show the area of this uniform distribution is 1. How long will a student typically have to wait for a bus? What is the probability that a student will wait more than 25 minutes? And what is the probability a student will wait between 10 and 20 minutes? All right, so the first thing it said was to graph this. Now, it's already told you that we are using a uniform distribution. So I'm not going to redraw it. So to draw the graph, what would be my minimum point?
0.
In this example, 0. And the maximum?
30.
30. Now it says, show that the area of this uniform distribution is 1. All right, now here's where we are going to use some formulas. Look at step 2. The time student must wait for the bus are uniform between 0 and 30 minutes. So what formula are we applying here?
1 over B minus A.
I am going to redraw this just a little bit smaller. Is that picking up?
Yep.
How about that?
Nope.
Now we good?
That's good.
All right, so point A we said was 0. Point B is 30. So step 2. We are asked to show that we are uniformly distribute at 1. All right, to show that the area of distribution is 1, what formula do we apply?
1 over B minus A.
What's the formula for the area?
Height times base.
Length times width. Height times weight.
All right, now how can we apply that? Let's apply this to a formula.
1 over B minus A times base,
1 over B minus A.
which is 1 over 30.
What else do I have to add here? Multiplied by B minus A. All right, so if I solve for the area, what's my point 1?
So B is 30 minus A, or 30 minus 0, times 30 minus 0.
And if you solve for that, you're going to get 1. In 3, how long will a student typically have to wait for a bus? In other words, what's the mean waiting time? All right, if you look back on page 207 at the bottom, you are given the mean of a uniform distribution. What's the symbol here?
Mu.
Of the mean of what?
Sample. The U is the population.
Mu. So the mean of the population of a uniform distribution is equal to
X bar is sample, right?
X bar is the sample mean.
That's kind
All right, so now let's plug this in. What's point A?
0.
Plus point B is 30. Divide that by 2. Now, what is the standard deviation? if you look at page 208, at figure 7.2,
The square root of b minus a squared over 12.
square root of b minus a squared divided by 12.
Charlie, is that 12 a constant in that formula? So that is the formula as it is set, correct? That's not going to change. 12 is not going to change.
No. Good question. All right, so plugging in for this formula. Point B, 30 minus 0 squared divided by 12. And we're taking the square root of that.
Two.
8.66. Now, in question 4, you'll have a homework problem like this. And question 4, what's the probability that a student will wait more than 25 minutes? So in this example here, if this represents 25 minutes, I'm trying to say what is the probability that a student will wait within this range? So what's going on here? So you're going to say, what's the probability 25 is less than 30? So what you're asking now, go back to where we solved for area here. But now you're just trying to determine what area is represented in this between 25 and 30 minutes.
A and B maybe. That'd be 25 be an A.
So 1 over
1 over 30 minus 25.
30 minus what?
No.
0.8 is 0. Now, here's where you're going to concern yourself with this range.
5.
So you would have 30 minus 25, or 5. In the first example, remember, we were looking at this entire range. .1667. As I work lower, is it still picking up on the recorder?
So you wouldn't start, the A would be 25 and the B would be 30 on the new formula. You would go back to the old, the beginning formula and your 25A and your B30 and start over again, you would do it like this and just times it by
Remember,
5.
before, we're looking at the entire area from here to here,
Right,
from point A to B. Here, I'm only looking at the area from here to here.
right. So you just don't, you don't start over. You just start like that then. Do you see what I mean?
No, I'm unclear with what you mean with starting over.
25 doesn't become A, even though you have the.
You don't revisit up here.
Yeah, that's what I'm trying to say.
No, we've already solved for this. It's
Right,
two different questions.
right. But you don't go back and.
Yeah, I think she was thinking sort of like I thought at first, because I
Yeah.
was thinking that 25 was the new A.
Yeah,
In this problem, that's why I said 25, or 30 minus 25 instead of 30 minus 0, down there on 4.
I get what you did, but I'm just saying that.
I understand what you did too, but like in my mind, on number 4 down there where you wrote 1 over 30 minus 0, I just saw 25 as the new A. That's why I said 30 minus 25 in the first part, not just the second.
No, we still have to take this whole thing into consideration, and now saying out of this, what's the probability that we're within here? And in part 5, we say, what is the probability a student will wait between 10 and 20 minutes? So now, here. What's the probability that we are within here?
Oh.
So now we're going to say, what's the probability within 10 and 20 minutes?
So it would be 1 over 30 minus 0 times 10?
And Wisconsin, did that pick up? Are you picking up low on the board?
Yep, we can see all the way down to the tray.
All right, well, I know my writing range right now.
So you can say 33.3%.
Probability that students wait between 10 and 20 minutes.
Is 33.3%.
There's a 33.3% probability that a student will arrive and have to wait within 10 or 20 minutes.
Now, I know these are, like, they're gonna get more difficult where you can't do this, but immediately when you said between 25 and 30, I seen that was 1/6 of your time frame there. And that's 0.1667, correct?
Yeah.
That would be 1/6.
No,
Just as that 10 minute, between 10 and 20, that's 1/3 of the total amount of time you have there, which is 1/3, 0.333. Is that not true?
In this example, that will work.
But it won't work because the numbers are going to.
I want you to learn,
The concept.
yes, if that'll help us sink
The
in,
steps, yeah.
go through and kind of visualize what we're hitting. But yes, good observation. Now tell me, why would this be useful? Why would this be useful to the school?
Would they adjust their bus schedule based on some of this information?
Good point, yes. Think of you as being at a school. No one wants to have a student coming there and having to wait any longer than is necessary. I mean, there's several reasons from convenience to safety. And I think, didn't it say the buses ran
Every 30 minutes, I think?
every 30 minutes to 11 p.m.? Ladies, would you like to be sitting at a bus stop at 11 at night, waiting for 30 minutes for a bus? Guys, would you? You want to get home and watch or play fantasy football? All right, so for adjusting for convenience, safety features, you want to know, if this was, and this is pretty promising, between 25 and 30 minutes, 17% of your students are waiting during that time period. 33 are waiting here, so a majority are waiting less time. Now, I don't know what the goal would be, but I think in general, broad terms, shorter is better than longer here in this example.
Can you do example from 0 to 10? Let's see for probability.
Would be the same here. If I
Yes.
look here to 0, I'm
Yes.
still.
So more student waiting.
All right, what are the characteristics? I'm gonna flip over to page 212. Tell me, what are the characteristics of a normal probability distribution? So you're gonna hear this term, a normal probability distribution.
It's bell-shaped and symmetrical.
G-halves are identical.
All right, first, how's it shaped?
Bell-shaped.
All right, so we're gonna say first. Bell-shaped. See where it starts small, it goes up to a peak, and then we come right back down. What's the second?
Symmetrical.
It is symmetrical. It is evenly split into two halves. What is it symmetrical around? What identifier could I put here?
Median.
It is first, the mean.
Mean, median, and mode are
All right, we're gonna focus on that first one. It's the mean. And what is the next characteristic here?
I tell you, I don't know if I pronounced that, sir.
Give it your best.
Asymptotic.
Good job. Asymptotic. Okay, what this means is that as the distribution comes down, it never truly touches the x-axis. Well, what is it going to do? Kind of comes right here, just above it, kind of hovers around it, and it's going to go out. It's never going to actually touch the axis.
Stay parallel.
It's going to just kind of run parallel to it. So once it comes down to this lowest point, it's just going to continually run out. And if you look in, notice that when I showed that it was split and symmetrical around the mean, median, and mode, what total area is under this curve?
underneath. Is that what you mean?
No, what total area falls within the curve? One. All right, so everything in this curve, and notice I put 1/2, 1/2. Everything under this curve equals 1. And if I split that, remember, the total area under the curve is equal to 1. I have 1/2 to the left of the mean. I have 1/2 to the right of the mean. All right, and if you look at there on page 212, you're going to see another chart containing all of these characteristics. If you look at the top of 213, you're going to see various types. So remember, my bell-shaped, it looks something like that. I could really peak in the middle, as long as I still have these three characteristics. I'm still going to meet this definition. All right, and we're back. All right, the standard normal probability distribution. Let's flip over to page 214. And what is the standard normal distribution?
And then it had like a rating. I don't know, so many.
The problem was
That's too high, we can't see it.
That's too high?
Yep.
Well, it's below my line that you gave me last time.
There we go.
I'm going to have to draw my line higher. All right, so what is the standard normal distribution? The top of page 214.
Mean a 0 and a standard deviation of 1.
Well, let's look. The number of normal distributions is unlimited. So remember, we would be within that range, and anything I pulled out of that range, I would have a bunch of, really we'd have a bunch of stuff that looked like, because every 2 points that I went to, I'm going to have a different distribution. All right, so because the number of normal distributions is unlimited, each having a different mean, standard deviation or both. What are we told? We need to convert this into a standard normal probability distribution. All right, now by doing this, we are going to be subtracting the mean from each observation and dividing the difference by the standard deviation. Okay, now I'm going to say we are going to use something called the Z value. And what is the Z value equal to? X, which is the value, which is your observation value.
Minus the population mean.
Minus the population mean.
Divided by the standard deviation.
Divided by the
Standard deviation.
of what? Standard deviation of the population. Remember that symbol would have told you the value of D. All right, and if you want to look at the bottom there, 214, here you're going to see an example, statistics in action.
What is the standard deviation sign for sample? I forgot.
Go back to your cheat sheet. All right, on page 215, here's the problem. And we know, we just said that the value all right, so we know it's got a mean. Let's see here. Yeah, 215. Okay, so the weekly incomes of shift foremen in the glass industry. All right, so foremans in the glass industry. follow a normal probability distribution with a mean of 1,000 and a standard deviation of 100. What is the z-value for the income? All right, they're going to call this the z-value. A foreman who earns $1,100 per week. Okay, so what would be the z-value of a foreman who earns $1,000 a week? So in this example, we see that the mean is 1,000 and the standard deviation is 100. And we want to know what's the likelihood that a foreman earns $1,100. So this is 1,100 becomes our observation of X. So how would I solve for this?
Z equals 1,100 minus 1,000.
So 1,100 minus 1,000 divided by 100 equals 1. Now, interpret what that tells you. What does a z-value of 1 tell you?
Guarantee that. Oh, z-value.
Standard deviation of a z minus
C of 1 indicates that a weekly income of 100 is one standard deviation above the mean.
Okay, so for a z-value of 1 indicates that the weekly income of $1,100 is one standard deviation above the mean. All right, now I want you to flip the page to 216. And let's look here. We see that under, I'm going to put and if I go out one standard deviation on either side, how much data will I encompass?
68%.
68%. If I go out 2 standard deviations,
95.
and if I go out 3 standard deviations,
99.7.
99.7, or the book might just tell you practically all. I always remember it as 99.7. Now look, as we go out more and more standard deviations, look at what's happening. I'm including more of the data. Remember, I would never go up to 100 because we're never touching this axis. I can never say within probability measurements that I'm 100%. I mean, 100% it's guaranteed to happen. But I would never, if I was taking samples, I would never be able to say that I was at 100% because I'm not analyzing all of the data here. Remember, we're pulling. So 1 standard deviation out, we're going to include 68% of the data, 2 standard deviations out, 95%, and 3 standard deviations, practically all. All right, let's go back and look at one more example. Okay, the bottom of page 216. Okay. All right, as part of a quality assurance program, Auto Life Battery Company conducts tests of battery life. For a particular battery, the mean life is 19 hours. The useful life of the battery follows a normal distribution with a standard deviation of 1.2 hours. 68% of the batteries fall between what? So in this example, the mean was, is it 19 hours?
19 hours, yeah.
19 hours.
Standard deviation of 1.2 hours.
1.2 hours. And it says about 68% of the batteries fall between what two values?
No. Don't be too high. We take 19 hours, we plus or minus it by the standard deviation. 20.2.
Flip to the back of your text. Flip to the very back. I don't see an appendix number, but it's the very last page in my text right here. Let that be your guide.
Oh, right here.
Okay, so the first way to look at this, it says about 68% of the batteries fall between what two values?
19.
Okay, we know that 68% of the batteries are going to fall between one standard deviation of the mean. Your mean is 19 hours. Okay, so we know that 68% of the batteries will fail between 17.8 and 20.2 hours.
Right.
So remember, they're taking they're taking this plus or minus
Standard deviation.
the standard deviation. You would ensure that 95% of the batteries fail by taking the mean plus or minus, so plus or minus, two standard deviations. (16.6) and 21.4 hours.
Oh, okay.
And practically all batteries are going to fail between what? 3 standard deviations
So that's 3 deviations, standard deviations.
plus or minus the mean. All right, now I said refer back to this distribution. Let's go back to page 214. All right, this is appendix B. Text is saying it's B3, but it doesn't say B3 on mine. It's just the inside. It's on the inside cover, on the back cover. And I want to show you how to read this chart. So look along the vertical axis. And you're going to see z-scores ranging from 0 to 3. Everyone flip to the very back of your text.
Okay,
It's inside the page.
so these.
Right here, right here.
Okay. Oh, here's Z right here.
Okay, and I'm going to show you. Look at your z-scores of 0 ranging to 3.
Okay.
So when you calculate your z, let's say that we have to calculate z to being, let's compare it to this example, 1.5.
1.15.
So looking in the middle with a z-score of 1.5, how much area is under the curve?
1.5. Okay, is it the top lines or is it the bottom? This one's on the side, on the vertical on the in the side right here. This is Z's, right? So you mean Z's 1.5?
If z is 1.5,
Okay, gotcha. Z's 1.5, and then we're gonna look for that number, right? We're gonna look for the
and let's say that I go out to this 95%. So if 95% is under the curve,
0.4441.
remember, if 95% is under the curve, and here's the mean. Now, of that 95%, how much is going to be greater than the mean? Remember, a half of that. So half of the 95%. And then half of the 95% is going to be over here.